this computer. Okay, because you might, for those of you that have, like Abby, Nix, this may be a little more confusing as we're talking about it now. So if you can go back and reference it later, you'll hear it once, so you can go back and hear it again. That might be helpful to you.
Okay.
Just want to make sure it's recording. Okay. So let's look. It's like slow connection again. I don't know why. There we go. So it says a chemist does a rate analysis on the following chemical reaction. So we get a chemical reaction. We don't really actually have to worry about the chemical reaction too much for these kinds of problems. And then he comes up with the following data. So we are going to be looking at rate reactions. So you can look at there's a formula for the rate of a reaction. The rate, if you look in the beginning of the chapter, they talk about how rate can be measured in change in concentration of the reactants over or products over change in the amount of time. And so that might tell you at 30 seconds, you can get the rate of that reaction. At 1 minute, you can see what the rate of the reaction is. Well, the reason that's only minimally helpful is because if what we just talked about, as the concentration gets less, the reaction actually slows down. So as those reactants are getting used up, their concentration is going down, so the reaction is going down. So this is kind of a math concept. You know, when you're doing mostly in algebra, you're looking at linear equations, that slope stays the same. Everything is changing the same amount as you go down that line. But when you're looking at a reaction, it doesn't change the same. So that's what calculus is the study of things that don't change at the same rate. So you have an f of x and you get something like a hyperbola or a parabola. We're not going to have parabolas. I was trying to remember if a hyperbola is the one that goes like that. That's kind of what yeah, I think it's like that. Anyway, you don't have to worry about understanding the calculus part of it. It's just like big picture, 10,000 feet. Like that's just the difference. We don't have like a straight line change. We have a change that it's really fast in the beginning. So, second one, that speed's gonna be really high. But then as that concentration goes down, that speed's gonna abruptly start coming down. And the reaction's not gonna be going as fast. So it's helpful for chemists. We may not, you personally may not want, but for chemists, it's helpful to have an equation that describes how that reaction is changing at a given moment in time. And so there's envelopes up in the cabinet. You can go look for some. No, well, stop interrupting me. So they talk about this equation and it looks like this. The rate of the reaction, R, equals K, which is a constant, times each of the reactants. So in this case, I'm just going to write the reactants in. We have H2 is one of our reactants. And then we have a reactant NO. It's equal to both of those. And then those can possibly be increased, if we start too high, by an exponent X or Y. So that looks kind of complicated, but we're going to unpack it a little and realize it's not really too complicated. If I change one of those reactants and like if I double the concentration of a reactant and then the rate over here also doubles, this X is just a 1. But if something else happens, if I double my reactants over here, if I double that concentration, so I'm maybe at a concentration of 20 and then I double it to 40 and then my rate of reaction doubles, that's when this exponent's going to change to account, so let's say quadrupled. It didn't change 1 to 1. Then that's going to be where that exponent comes in. So we're going to look at this with actual numbers, so it makes a little more sense. I think like when you're just hearing it, it's like, wait, what? And as I was telling Abby the first time she heard this, like, just try to receive it and not get too like, oh my word, where are we going with this? Because it can feel a little overwhelming the first time you hear it. There was one other thing I was going to say. What was it? I guess we'll get to it. I don't know. I had a thought while I was talking and it left me. I know what I was going to say. This constant and this exponent X and Y, there isn't an equation that you can just say, there's a reaction, let me plug some stuff in and then I can get those numbers. You actually can only get the data experimentally. So that's why you'll see in these problems that they give you in this unit, this module, is that they give you kind of like, here's
what are you doing?
What's that? Oh. They'll give you a chart and it will just have like trials that are, like experimental trials. So you can't get these numbers unless, and it's science, it's chemistry beyond what we could do in this class. So we're not really missing out because we can't do lab. We wouldn't be able to measure these numbers in a lab anyway. It's not, we don't have the ability to do that in our setting. So as we just look at the chart, hopefully you guys are looking at your workbook. If you're not, it's probably going to be pretty useless to you, but I'm on page 350 of our workbook, looking at number 3, and they have 3 trials. And so what they're telling us here is what trial they did, and then what the initial concentration was of one of the reactants, or both of the reactants, and then what the reaction rate. So I know a concentration of hydrogen, concentration of nitrogen oxide, and then what the instantaneous reaction rate was at those 2 concentrations. And then they do that for multiple concentrations. And so then I have to look and say, what can I find out from that information? So I try to find a trial where one of those stayed the same. So like where the concentration stayed the same. So for instance, hydrogen, from trial 1 to trial 2, the hydrogen stayed the same. It did not change. So if there's any change in the reaction rate from trial 1 to trial 2, it's going to be a result of that nitrogen oxide. Since the one stayed the same, it can't have changed anything. But the other one did change. And so if there's a change in the reaction rate, it's going to be as a result of that nitrogen oxide. So I look and see a nitrogen oxide went from 0.3 to 0.6. So it doubled, right? I just doubled, the scientists that did it doubled the concentration. Does that make sense? Just from just what's happening there.
How do we know like what compounds we're using?
They would have to give it to you, Caitlin. They would have to give you they'll always give you the formula, and then they're going to show you like experimental data that was collected from experiments with that.
Oh yeah,
not something
just like an experiment tells you which.
Yeah, so it's like someone did an experiment and then they're giving you this data from their experiment, and then you wouldn't be able to figure it out any other way. You'd have to have this data. So we're just saying from trial 1 to trial 2 that nitrogen oxide doubled, the concentration doubled. I'm just observing that. I'm just saying I went from 0.3 molarity to 0.6 molarity. It just doubled. So I'm just observing that. So then I look over at the reaction rate, and I can see that I went from, and this is where I will tell you, I have even found this to be a little bit, even I, like I'm so smart, that's not what I meant, but I as a teacher, have found this to be a little bit tricky, not tricky conceptually, tricky in how they, like the book, when they give you the answer, how they do the numbers. So like, sometimes they'll round in ways that I'm like, well, you didn't have to round like there, but so all that to say, if you can show me, well, I could see that it tripled or quadrupled because of this, and show me the numbers, and you can validate what you did, I'll be more than happy to accept it, because I think sometimes it could go both ways with the way they do that. So that might make more sense to you as we go. So I look at this, I have 0.005, or maybe you could round to 0.006. And then I look at that second trial, and I have a reaction rate of 0.02. And so I could say from 0.06, or no, this is the one where I thought it looked like it. Hold on, give me 1 second here. The first time I did it,
would be 0.01.
Yeah, they go to point, that's what it is. So this is a good example of that. When I first looked at this, I said, oh, it went from 0.006 to 0.02. And that would be like it quadrupled, but that's not what they did in the book. They rounded it to 0.01 and looked at 0.02. That's what I'm talking about, that there's a little bit of variability in how you look at that. And they don't tell you round to the tens place or round to this place. So you have to kind of play around with those numbers, almost like we're trying to find the one that falls into something easily. So in this case, they took that point, and I think as you work these, you'll see what I mean with that. And again, if you did this one though, and you went with 0.006 and 0.02, and you're like, it quadrupled, and you show me that, I'll take that, because I think that's reasonable. It may not be what is exactly right for what they are asking you to figure out, but I think actually it's reasonable. And I'm wondering, actually, maybe if you have to use significant digit, I'm thinking out loud. Hold on. No, forget it. Don't think about that, because that's not true. Okay, so I was just contemplating. I'm such an out loud thinker. That's not great in a class. So in this case, they just rounded that reaction rate to 0.01, and then looked at the second one at 0.02 and just said it doubled. So what I'm observing is when the concentration of nitrogen oxide doubled, the reaction rate doubled. They changed at the same rate. Does that make sense to everybody? Abby Nix, I can't see your face, and I always usually judge by your face whether you're understanding or not. And Abby Houston, I know you've at least heard this one, so you've heard me say this. But so knowing that it just doubled, it changed. Whoops, I did not mean to erase that whole thing. Let me get my equation back here. Knowing that the nitrogen oxide, oh, wait a second. They are squaring that one. They didn't do it that way. I think that's how I did it the first time I rounded. Hold on, let me get my calculator out. I want to check something really quick here. Sorry, this is not an issue of understanding. It's an issue of trying to understand which way the book did it, because this has been kind of my biggest beef about this section. Hold on. Sorry, I'm just calculating something before I keep talking. Give me 1 minute. Sorry, I feel like I'm gonna confuse you guys. I think when I did this the first time, I was the one, I rounded. I said 0.01 to 0.02, it doubled and the other doubled. And so if that were the case, can you guys see my whiteboard okay? Yeah, I think you can. If that were the case, then this would be just raised to a power of 1. Sorry, it's super messy. It's gonna drive me nuts. However, when I went to go check it in the book, they didn't. They had raised it to a power of 2, and I'm like, what the heck? It looks like it doubled. And they indeed looked and said from 0.006 to 0.02, it quadrupled. And so they raised it. So when my reaction rate quadruples, but my concentration only doubled, I have to find that factor between the two. We're going to work more than one example, so don't worry.
Can you just put the numbers in and then try to explain it? Because when you're trying to explain it before the numbers are put down, I'm still just like, what?
Well, that's the thing. You get the numbers from the chart. So that I could just say, like.
I know, but like, what are the numbers? Because I know that, like, okay, it tripled here, it doubled here. Where do I put, like, what do I do with that? I
know. That's what I'm trying to, yes. I mean, I can, but so to answer that, Caitlin, if that were the case, like this, whoops, I keep hitting erase instead of the eraser. Sorry. If that were the case, like, so for this one, the reaction rate is just going to end up looking like this. But it's not such a simple thing to just say, okay, I can just look at something and say, where's the 2? Let me just find it on that chart. It doesn't work that way. And I think that's probably what's the hardest thing about this unit. Now, just to give you some peace of mind, this is about the most involved part of this unit in terms of math. There isn't really anything else besides this. Like, it's all, there's other conceptual things.
I have no idea what's going on.
What's that?
I have no idea what's going on.
I know. And I will say, like, I did work through, I'm not trying, and I don't mean this any sort of like, I told you so, but like, that's why I went through some of these in the video, like step by step. So what would have helped, like if you had seen the video, you would have seen it once, and then you would be seeing it again, and it would be simpler. And so for sure, I would expect it to be very confusing if you've not seen me do it, because even for Abby, like watching it that first time, it is confusing. The first time I read the book, I was like, what in the world are they doing? I don't even remember doing that in chemistry. Maybe I did it, but I just forgot. I don't know. It sounded very new to me. And then I had to read it again. And then I looked I looked at the example that they gave in the book, and I read step by step to see what they were doing. And I'm like, oh, okay, that's making a little bit more sense. And then I actually like wrote one down to see like, how exactly do you do this? And then my understanding increased a little bit more. I definitely don't think it's something that you just kind of pick up once and go, oh yeah, I got it. It takes, because you're analyzing something. That's what it is. You're analyzing something, and there is no equation just to plug everything in and say, okay, that's what the exponent will be. It just doesn't work that way. But what I wanted to say was the reason where that 2 comes from is when I look at those trials, I look and say, when I double the nitrogen oxide, again, we'll look at another one so that this can begin to make more sense, but the reaction rate quadrupled. And so I look at, what do I have to multiply 2 by, or what exponent do I have to raise 2 to get 4? I have to raise 2 to the 2nd power to get 4. And so that's what plugs in for that exponent. When I look at the hydrogen, let's just look at the hydrogen here, just to keep doing examples. I feel like we could dwell on just that spot, or we could just keep working examples. And
how did the reaction rate quadruple? And then, because it went from 0.1 to 0.6.
Well, that's what I was trying to say, and I think that's where I was confusing you. And what I would tell you, Caitlin, if you looked at that and you did, because that's what I did. The first time I did this problem, because sometimes they have done that on other examples, they've rounded like that. I did round to 0.01 and looked at it and said, okay, well, it doubles. And that's how I worked it. In which case, if the concentration doubled and the reaction rate doubled, if it did that, then this would not be a 2, it would only be a 1, which you wouldn't write it in there, because, right, if it's raised to the 1st power, you don't have to put it there. If you did it that way and you showed me and said, look, I rounded this, look, it doubles, I will accept that answer. I think that's very
I
reasonable.
don't understand why it's a 1 either.
Well, that's just saying, and this is where I would encourage you also to read the example in the book, because I think they explain it step by step very well as well. And there might be some way that they say it that makes more sense to you. But in fact, let me look at that real quick. But it's just saying that if the concentration doubles and the reaction rate doubles, they're changing linearly. They're changing linearly proportionally, like a straight line. Like the slope is linearly. It makes a linear line. It's kind of a math concept. So there, if you can't like quite grasp that, it's okay. I think you can still work the problem. It's just a math concept to say they're changing the same way as they change. So when I double concentration, reaction rate doubles. But sometimes I'll double the reaction rate, sometimes I'll double the concentration and the reaction rate doesn't change at all. We'll talk about that in a moment. Sometimes I'm going to double the concentration and the reaction rate is going to quadruple. It's not going to just double, it's actually going to quadruple every time. And so we have to account for that. And that exponent is what accounts for that. Do you guys mind if I take a call from Delaney real quick? Does anybody care? She's trying to get me something at the store. Hey, can you tell me quick? Oh, I'm on my class. Yeah. Yeah, probably. Yeah, go. Yeah, just go ahead and get those. Okay, bye-bye. So again, we'll look at some more examples so you can see that in action. But what I'm trying to say also is if you evaluated those numbers, because again, this is analysis, there is room for people to analyze a little bit different because you are rounding numbers. So if you looked at this particular one and you said, yes, I see 0.01 and that is doubling because the next one's 0.02, I would accept that. So if you can validate what you did to get those numbers, I'm good with that.
So it didn't change in this first one, and then it tripled for this first column. Then the second column, it doubled, and then the third column, it doubled and then tripled. I don't understand.
So let me back up. I think I can help you get somewhere with that. So when you make an analysis, you need to find 2 trials. So you always want to just be looking at 2 trials. Just compare 2 trials, and if you want to find 2 trials where one of the reactants stays the same. So yes, hydrogen does triple, you're right. And we're going to look at that because when the hydrogen triples, if you look over there, the nitrogen oxide does not change. So that would be 2 trials that we could evaluate, which we'll do next, to evaluate what impact the concentration of the hydrogen has on the reaction rate. So yeah, don't look, you can't, it would be hard. Yes, when all those things are changing, you can't make any analysis because too many things are changing. It's like having a control in an experiment. You have a control, you know, like when Wolf has his allergy testing, they do just one where they put like just whatever, the stuff that makes you react. The histamine, they'll put just one spot where there's just histamine to see, does he actually react to histamine? So that when I look at all the other ones that are different materials that have histamine in it, do they react? So you always have a control, something that is something you know. So in this case, you have to have something where you know that did not change. That's kind of the control. It's not the exact same, but where something's not changing so that I can attribute any change to the thing that is changing. So just 2 trials. Hopefully that would
have been helpful if we started with that.
I said it, but I think there's just, I remember saying it, but there's just a lot of information. So when you're trying to take in lots of information, your brain doesn't process all of it. So it's okay to say it again, but ask those questions. I don't mind clarifying it. Sometimes it's just how I have to figure out what's the thing that you're confused on so I can clarify it. And you ask good questions because
step 1 is figure out which 2 things we're looking at, and we're looking at the NO and the reaction rate.
Yeah, we're looking at the reactants. We want to find 2 trials for each of them where only one is changing. So that's why for trial 1 and trial 2, the nitrogen oxide is changing. So that's why we're doing our analysis there. So then we can go ahead and go ahead.
The NO doubled in this because it went from 0.3 to 0.6. So we put the 2 up there.
Not because that doubled.
And the reaction.
Not because that doubled. I have to look at the relationship between what's happening. So I have to evaluate that it doubled, but I have to look at it in relation to what happened to the reaction rate. And that's where the exponent comes from. not just that it doubled. So I don't look and say that doubled and plug in a 2 for that exponent. I have to see, did the other one double? And then I see, okay, they both just doubled. They changed in the same way. One doubled, the other doubled. They changed linearly proportionally.
What if they weren't the same?
Then that's when the exponent changes. So let's look at, well, in this case, the way that they evaluate, the book, the author of the book, the way they evaluated those numbers, they looked and said that the reaction rate quadrupled. So if in fact it quadrupled, so let's just say it quadrupled, we'll just accept that. Concentration doubled, reaction rate quadrupled. We can mess with numbers later, but let's just say, because that's what they're saying, that it quadrupled. So if that's the case, I have to look at what does that concentration, so when I'm saying the rate equals this constant times this concentration, I'm not multiplying just by that concentration 0.3, but I have to change it by a factor based on what I observed experimentally to say it wasn't just a 1-to-1 ratio there. It was a 1 to, would it be 1 to, I didn't want to say it that way. I'm gonna get mixed up on my ratios. When the concentration doubled, the reaction rate quadrupled. And so that tells me I actually need a 2 there. The 2 has to be squared so that I can get to quadrupled. 2 to the second is quadrupled. Let's look at some more where that changes so you can just see it a few times. And I think
so it's a 4 because 0.5 times 0.567 times 4 is the 0.022. So that's a quadruple. Right. And then you're dividing the reaction rate by the initial concentrations, which is a 2, and that equals 2.
I don't think it's always like that though. I think if it went like a higher exponent, I have to look at my math like on paper. I don't think you could divide. You have to say, what do I have to, that shouldn't.
Well, it's a ratio.
Yeah, in theory that should make sense. Yes, in theory that should make sense. I'm not very good at thinking about it in my head versus paper. I think that would make sense. So we can just test it out and see if that rule works. But yes, because they explain it and saying what factor, what do you have to multiply 2 by? Hold on, I want to look at something in the book real quick here. Give me 1 sec. I want to clarify something here. Let me see that.
So we literally only have to find the exponent, and that's what we do for our problem?
Yeah, well, yes and no. So in this case, yes, you find the exponent. So let me not get stuck here. Let's put that 2 in there. There's one more step because they're asking you what is the reaction rate for this equation. I'll explain that in just a second. So let's look at that. The hydrogen's easy. Like you said, in trial 2 to trial 3, it triples. It goes from 0.7, they just triple the concentration. And then 0.02268 to 0.06804 it also triples. And so if one triples and the other triples, it's just a 1-to-1. It's changing the same way. And so hydrogen just has that exponent of 1. Again, you don't have to write that in there, I'm just putting it there. Now, the last part of this is what they want is a reaction rate equation. So I need to know what the constant is for this particular equation. So then I can take any one of those trials and I can plug in everything I know. I can plug in the reaction rate because I have that. I can plug in the concentration of hydrogen and the concentration of that nitrogen oxide.
I can do any of the numbers anywhere, or does it have to be from the same column?
Well, it has to be from the same trial. So I have to say when the concentration of hydrogen is this and the concentration of nitrogen oxide is this, then the reaction is this. So they have to be from the same trial. So if I put in that trial 1, I would just say 0.05670 is equal to K times concentration of hydrogen, which was 0.7, and times the concentration, and again, it's only raised to the first power, so nothing's happening exponentially there, times 0.3, and that's squared. And then I'm just solving for K. So hopefully that solving is not too hard math-wise, right? You're just gonna divide both sides by that. And then that gives you K. And then to give the actual answer, so they ask you, what is the rate equation for this? So that K ends up being 0.090. So if I want to write out the actual answer, I would say the rate at a given moment in time is going to be equal to this rate constant, 0.090. And that should come out the same, that should come out the same no matter what trial you plug in there, because it is a constant. So I just switched colors. That color's change is not significant. I just accidentally grabbed the wrong color. 0.090 times concentration of hydrogen times, that's a 2. I don't mean to be so messy. I'm trying not to rest my hand down and mess up the screen. Squared. So that right there is the actual answer to that question. That is the rate reaction for that. I know this seems like it took a long time and it was really hard, but when you understand it, it won't take you that long and it won't be that hard. It's just like riding a bike. Like it feels really, really hard because you're like trying to move everything together and coordinate it. So don't feel like my homework's gonna take me. Oh, Wolf, run and go get my power cord for my computer. It's up next to my bed. Can you run? Because my battery's about to die. Like I didn't realize how low it was. Like, can you run? Get it before it dies. Once you have understanding of it, they won't take you this long. I promise you, they won't take you this long. It's just like getting into the hang of it. So the next one is same kind of problem. So let's just work that one together. I'm taping this, so you'll be able to go back and get that. So they just tell you about the equation, the chemical reaction, which is irrelevant really to what you're doing. But ozone can be destroyed by certain pollutants, one being the nitrogen dioxide that is expelled from the exhaust of cars and planes. The reaction that governs this process is. First part doesn't really matter to us in solving this problem. A chemist does the following experiment to determine how fast this ozone destruction occurs. So they basically give us the concentration, so it looks just the same as last time. Okay, can you plug it? Seriously, buddy, it would really be annoying if my computer dies and I have to get back on here. I'm moving like a sloth. What's up? I appreciate you getting it, though. Thank you. Well, come on. For the love, hand it to me. Is it all connected? What was that other cord? I don't know. Okay.
In this one, though, there's only one column that has a period where it doesn't change, so we can only get one.
Well, actually, let's see here. Let's see what we've got. So if I look at trial 1, nitrogen oxide, so I can find that trial 1 and trial 3, it's not changing. And for the ozone, in trial 2 and trial 3, it's not changing. So try to just look at you're used to kind of looking across to see what happens in a particular trial, but look just down in the column. So if you can see trial 1 and trial 3, nitrogen oxide stays the same. So you can use that to figure out what ozone does. And then you can look at in trial 2 and 3, the ozone does not change. It stays at that 0.00002. And it does change for the nitrogen oxide. So that's where I can figure out what happens in nitrogen oxide. So let's just look at the first one, that first reactant, nitrogen dioxide. So I need to find where nitrogen dioxide is changing, but ozone is not. So ozone doesn't change in trial 2 and 3. Can you see that, Caitlin? Does that make sense?
Yeah.
Okay, so I'm looking at trials 2 and 3. You might just cover one up so you don't get mixed up with what you're looking at. And so I see that nitrogen dioxide doubles. And then I see real easily in this one, it's nice to just give easy numbers, that it doubles, right? So it just changes linearly. So my exponent is 1. So far what I have is reaction rate equals the constant times nitrogen dioxide to the first power. And I'm just putting that 1 in there as a placekeeper, just to like organizationally tell me, okay, I've addressed that reactant, so I don't have to think about that one now. And then I look at ozone. What are you doing? Hang up. It's so distracting. Can you just go in another room, please? And she's trying to do stuff.
I know, I
Give me
should
my
ask
phone.
her what time she'll be home, but she never answered me.
Go find what you need to do.
I can't.
Go get on Khan Academy and do math. Ask Dad to log the computer in
Dad's
for you.
upstairs on her phone.
Then just go away for a minute, or go do it on that computer. No, it's not.
Yes.
So the ozone, if I look at the ozone, now I'm looking at trials 1 and 3 because the nitrogen dioxide stays the same. So I know that any change between trial 1 and trial 3 is due to the ozone. And I can see that the ozone doubles. But then here's the interesting thing. The reaction rate did not change at all. So what that tells me is that the concentration of the ozone has no impact on the reaction rate. And so it kind of falls out of the equation. And the way that it does that is it's raised to a power of 0, meaning it has no effect. And do you remember what something raised to a 0 power is equal to? That's right, it's equal to 1. So that's where it doesn't actually then affect the reaction rate, because every time, no matter what the concentration is, it's just going to be multiplied by 1. So you can, if you don't understand that, it's okay, but what you could just go from memory just to say, okay, when the concentration changes but the reaction rate doesn't, there's no impact, I just raise it to the 0 power. So that is like something you can say, like that will always be true. So then at that point, I'm done with that one, except for I just need to find what K is. And so I'm going to pick a trial. So I'll pick the second one just because I can. And I'll say the reaction rate 0.044 is equal to K times point. I don't know why they didn't do these in scientific notation, but they didn't. So, and then just times 1 because, or no, sorry. Yes, times 1. That is true. And then I just solve for K. And K should come out to 880 actually in this one.
And then we're left with R equals 880.
Yep.
NO times NO2.
Yeah, that's it actually, because it's raised to the first power. So that is a reaction rate for that equation. Yeah. So much simpler one perhaps compared to the other one. Give us a third example.
Yeah.
Well, if you don't know. So in extra practice problems, they don't give any more of those. I actually put a few, or not extra, on your own. I put a few of, and remember these on your own, they give some explanation in the back of the book. So I think they do a pretty good job. Sorry, I was going to say something else. They do a pretty good job of taking you step by step through that. So you've seen it, you can work it, and you can look at their, if you're still confused on it, you can go back and reference that. That's not your homework, but you can go back and reference that. I did add a few of the extra practice problems that, because in the study guide, I don't think, you know how the study guides really goes more through like just, study guide goes through more conceptual stuff in the chapter. And I wanted to make sure you had a chance to practice those this week and next week instead of waiting all the way till next week when you got to the practice problems. So I just grabbed a few, like maybe 3 of the extra practice problems and assigned those with the study guide. Study guide's not hard at all, so that shouldn't be any more taxing on you. I just want to make sure you get a chance to actually try those instead of waiting a week before you do them, so we can address it again next week if there's some confusion. So so if we keep going in the on your own problems, the next problem asks us about something that really just has to do with terminology. So it says the following reaction, and it gives a reaction, is determined by experiment. And that means like what they were just doing in these other problems, these trials, to be, let me just read it and then I'll tell you what's going on. To be second order with respect to the phosphorus oxide, and third order with respect to bromide. What is the rate equation? What is the overall order of the reaction? Okay, this is actually a very, very simple thing. It just sounds like a lot of wording because it's maybe wording you just aren't familiar with. So if we look at, let's look at the first one we did, just because there's more stuff involved. I'm just gonna write down the rate reaction for that first one we evaluated, which was R equals 0.090 times the concentration. So I'm just writing this down from number 3, just so I can teach you about that order stuff. Concentration of hydrogen times the concentration of, okay. So this order business is just terminology that chemists use. And so they will say that this reaction rate is first order, because technically there's a 1 there, is first order in relation to hydrogen, and it's second order in relation to nitrogen oxide. It's just referencing those exponents. And then it says, so the total, what is it? The overall order of that reaction is just the addition of those exponents. So the overall order is 3. It's just terminology. So then they want you to take that information and be able to write a rate reaction. So if we look at the problem, they give us a reaction. So we need to take those, we just start writing out our rate reaction. We know that, okay, so this is something separate. I'm working on number 5. We know that rate reaction is going to be a constant times the concentration of the reactants raised to a certain exponent. And we're going to get those exponents just from this order information that they give us. So I know that phosphorus oxide is going to be there. I know the bromide is going to be there. And I'm just getting that from the reaction. And then it tells me that it's second order with respect to phosphorus oxide. So what do you think the exponent would be if it's second order? Yeah, it's a 2. And then it says that it's third order with respect to bromide. So does anybody else besides Abby, because I think she gets this part, know what, or Caitlin, I mean, or Abby, gosh, can I get my names right? The bromide, if it's third order, what would that be? Its exponent.
Oh.
Yeah, it would be a 3. It's just saying, it's actually very simple. It's not.
Yeah.
That's what I mean. It sounds like a lot of words. And if you didn't know what the words meant, it would be difficult. But as soon as you know what they are, it's not hard. And then the overall order of the reaction is what?
5.
5, yeah. That's all that's going on there. And in this case, you cannot write a rate reaction where you know the constant because they haven't given you enough information to figure that out. They would have to give you some trials that you could plug in there. You can't. So this is as far as you can get is R equals K times those concentrations and the, because that might be a question you asked before we figured out the K and plugged that in and then said, that's what the rate reaction is. This is still a rate reaction. This is just as much information as we can get from what they've given us. So that's all. So once you read that, you've heard it, you'll go back and read it. And I don't think that order business will be anything complicated. The second, or number 6 is another question in reference to that order. Gives us a reaction, just one with more letters and numbers. And it says it's determined to be 4th order. So with respect to the C7H15Cl and 0 order with respect to the Na or sodium fluoride. What is the rate reaction and what is the overall order of the reaction? So same thing here. Just writing the rate reaction is equal to K. I start plugging in the reactants. I mean, that's just
wait. For the other one?
Yeah.
I didn't get what the rate oh, never mind.
You
never
sure?
mind.
It's okay.
Yeah.
Ask it. You sure?
No, I got it.
Okay. So I'm writing in my, I just spit on there. I wonder what that looks like on the camera. Okay. So see, I'm just writing in my reactants because that's always going to be the first step. Times the next one, which is NaF. And then I look and say, okay, what are the orders that give me? 4th order with respect to the first. So what's its exponent, Emily? Sorry, I put you on the spot. I didn't actually mean to. I just want to make sure you get it. Are you muted?
You said 4th order with respect to the first?
Yeah. Oh, wait, what did you say? Say it again.
You said 4th order with respect to the first.
Yeah, it says it's 4th order with respect to that C7H15Cl. So what would the exponent be then for that reactant?
It's going to be a 4.
Yeah, it's just going to be a 4. And then it tells me it's 0 order with respect to NaF. So what's the exponent for NaF? It's actually 0. Yeah, and otherwise equal to 1. So the overall rate, I'm just going to erase instead of rewriting.
Is it 4 or is it 5?
For the first one? Are you asking what I wrote down or are you?
No, the overall order is a 4.
For the overall order.
Overall order would be 4.
Okay.
Because it's 4 plus 0. So yeah, it's just 4. Okay, so that's all that. They really don't get any complicated than that. That's as simple as it gets with that, or as hard as it gets with that, rather. As simple as it gets would be a different reaction or different response.
That is not bad at all.
No, it's not bad. So number 7, yeah, those charts and evaluating that is really as hard as this module gets. It's really not a bad module. I just think your first encounter with it can be a little like uncertain. And then as you analyze it a little bit, you realize it's not that bad. It's really not bad at all. If you do the homework and you read through it, I think you guys will get it without a problem. Okay, so number 7 says, a chemist runs a chemical reaction at 100 degrees Celsius and determines the instantaneous rate to be 0.24 molarity per second. She decides to speed up the reaction by running it at 180 degrees Celsius. What is the new reaction rate? So the answer to figuring this out is just based on some information they give you on page, what is that? It's a very simple, well, it is a simple way to figure it out, but let me talk a little bit about something. So we talked about how reaction rate is affected by temperature, right? If it gets warmer, reaction rate speeds up. But then we do this reaction rate problem, and I don't know if anybody noticed, probably not, because you're just trying to think through the mechanics of it, but it doesn't seem to account for temperature. So if reaction rate is affected by temperature, one would think that it would be included somewhere in that reaction rate equation. And it actually is accounted for, but just not in a way that we immediately see. It's actually accounted for in the constant. So the constant K is a constant, but it's constant at a given temperature. And so if you read through like pages 508 and 509, they talk about how K changes as temperature changes. And so again, that's not something you can know necessarily unless you do it experimentally, but then they point out that, where's that at? That the rate of many chemical reactions doubles for every 10-degree increase in temperature. So
Yeah.
you remember seeing that? So when you get a problem like this, they're just saying, okay, at 100 degrees Celsius, this was the rate. So 0.24 molarity per second. But then I see that it raises up to 180 degrees. So there's eight increments of 10 degrees, right? So it doubles.
Oh.
It doubles every time. So the way you would write that out,
16.
you're just going to actually say 2 to the 8th.
Oh.
It's doubling. So, 2 times 2 times, it's
Yeah.
for each one of those 10-degree increments. Does that make sense? Emily, does that make sense to you? Okay. So it's as simple as that. So if it was 0.24, it ends up being 61. So if that were the case, it really speeds it up. That's a significant difference from, oh, Jonathan, or no, that's Abby. That's funny. I had Jonathan's name there for a second. I was like, okay. So that is that. That's number 7. And then number 8, I think, is a similar, but they go the opposite way, I think.
What did it equal to be?
61, when you round it to 2 significant digits, comes to 61 molarity per second. So number 8 is going to relate to that same concept. They reference back to question number 5. So we'll go back to that reaction. Oh, they give it to us again. Okay, so you determine the rate equation. And yes, we did determine R equals K. And that first one raised to the second one raised to the third. And then they ask us, if a chemist runs this reaction at 30 degrees Celsius with reactant concentrations of 2.0 each, and then runs the reaction again at 0 degrees Celsius with the same reactant concentrations, what will the reaction rates be in both cases? The rate constant for this reaction at 30 degrees Celsius is 1.25. So kind of a, what's that?
Are you going to multiply it by 2 to the -3?
Actually, yes, but actually, is that, I was trying to write this out mathematically, and so yes, you're on the right track, Caitlin. So let me just do it step by step for everybody. I was trying to think, I knew what to do. I can get the right answer, but I wasn't trying to write it correctly math-wise. Like they wrote it out, it ends up looking like this: 40 divided by 2, divided by 2, divided by 2. So would that be the same? I'm not sure if that is, or is there one more? No, I think it's just 3, isn't it? But mathematically, I had to think about how to write that down besides that. Like I can do 40 divided by 2 is 20, divided by 2 is 10. I kept writing out other ways and it wasn't giving me the right way. The simplest way was just, I know there's a way to write that. I'm not smart. I have to think about it to think what that is. But, okay, so let's just start at the beginning. So I'm kind of jumping ahead. So for some people that are less certain about this one, that might be confusing. So first of all, it says she runs the reaction at 30 degrees Celsius. And that, again, that's not going to be in the, they just tell me the constant at 30 degrees Celsius is 1.25. So then I know what to plug in for K. So I'm just going to say reaction rate equals 1.25. And they tell me the concentration for each is 2. And then I'm just taking that exponent from the original equation. I don't know if you guys caught that. Well, they gave it to you up there, so it doesn't even matter. And so I just solve for that. And that gives me R equals 40. And then what was, and then that's when they say, again, at 0 degrees Celsius. So now I'm actually decreasing the temperature. So you're right, Caitlin, you're dividing. Instead of making it faster, it's dividing in half each time. And there's, let's see, 3 increments of 10, right? So it's 3 times that it goes in half. And so that's where that divided by 2 divided by 2 divided by 2 divided by 2. And that ends up giving me 5 molarity per second at 0 degrees Celsius. And then they ask kind of an odd question. If you see it, great. If you don't, I'm not so much worried about you understanding this part, but why do the units and the rate constant include molarity to the 4th in the denominator? And that, let's see here. That comes from order. So like, I'll explain this, but I don't really, I'm like not gonna put it on the test. I don't really think it's too big of a deal, but so if I look at this equation, both of these are molarity, right? In terms of units. So I'm going to get a rate reaction that has molarity to the 5th in it. And so the constant K has got to be equal to something that has n to the 4th. Its molarity is actually in the denominator. So that I'm left with just molarity as a final unit. I don't know. I read that, I was like, I'm not really sure. I mean, yeah, I guess it's.
So what would we put down?
But I'm not really that worried if you're like, what in the world? I mean, it's just a unit. I think more than anything, it points out that the units for K, if you took anything away from that, it would be that the units for the constant have to do with the order of the original equation. That would probably be more helpful than, I mean, because that's what it's saying. So it's a constant, but its units can be different. It's molarity, whether it's to the 2nd, to the 3rd, cubed, to the 5th, related to what the order of the equation is. So don't get too hung up on that. If you're like, what in the world is she talking about? They talk about it in the book, but don't get too hung up on that. You don't think it's that big of a deal. All right, and then the last part of this chapter, they talk about catalysts. A catalyst is just something that makes an equation go faster, or not an equation, a chemical reaction. And the way it does that is it actually lowers the activation energy. So if you remember those charts we looked at where you started out somewhere and then it had either like a really big activation energy or maybe it had a smaller activation energy, and you could evaluate that from that bump at the beginning of the reaction, how much energy it was required to get that thing moving. So a catalyst just decreases that activation energy. And they really don't give you a ton of information about catalysts, so we're not really working with them in terms of any kind of mathematical analysis or even really stoichiometry or any of that. They want you just to recognize that change in activation energy. So like number 10, did I skip one? Oh, I'll go back to number 9, just a second. Number 10 just shows you 2 diagrams, one with that little bump and one with that big bump. And they say, which one represents the if that's the same reaction, which one represents the reaction with the catalyst? What do you think? Besides Abby Easton, because I know you know.
Wait, can you say it again?
Yeah, if you look at those 2 graphs for number 10 at the top of page 353, there's one with kind of that little bump, and then there's one with a real big bump. So if that's the same reaction happening, which one of those is a catalyst involved, do you think? And Emily, you were saying number 1. What, Caitlin?
A.
Yeah, it is A. It just has that smaller activation energy. So we see a catalyst is making the activation energy smaller. So that's just recognizing that is kind of all they want you to be able to recognize that. And then they talk, I'm going back to number 9 now. I skipped ahead in what I was talking about. They just say to catalyze the following reaction, to give the reaction, they say solid platinum is often used. Is the platinum a heterogeneous or a homogeneous catalyst? So they describe the difference between these two. You can have a homogeneous catalyst or a heterogeneous catalyst. All it has to do with is being in the same phase. So in this case, all those reactants and the products are all gases, and then they're using this solid platinum. It's a different phase, solid versus gas versus liquid. And the fact that it is in a different phase means it's a heterogeneous catalyst. If it were in the same phase, and actually, because what you'll see, sometimes there's 2 steps, and they describe this in the book real well, but you might have a reaction where you put the catalyst in there, and there's an intermediate reaction. And so while something's getting used up in the next part of the reaction, it's actually being produced again. And I think I failed to mention that the catalyst, it speeds up the reaction, but it never gets used up either. That's its other piece of a catalyst. So you might see it in the beginning and then you see it at the end too. So they give you a question like number 11, and they say, identify the catalyst in the following reaction. And so in this case, this is most likely, it doesn't tell you what phase these are all in, but we've got water and iodide ions. So they're probably dissolved in that water. So everything's, or sorry, that's peroxide, not water. Water's in the second step. So everything's in the same phase. So this is a homogeneous catalyst. So you're just looking for the thing that is there in the beginning and is still there at the end. So we have peroxide in step 1 and iodine ions at the beginning. We have an intermediate reaction there, those products. And then we have step 2 that takes those products and they become the reactants now. And they react. And then we have the final product, which is 2 water, an oxygen molecule, and 2 iodine ions. So if you look, the hydrogen peroxide is not there at the end, but the iodide ions are. So that's what the catalyst is. Does that make sense at all?
Yeah.
You're just looking for what's there at the beginning and it's still there at the end.
So the 2I is the catalyst?
Yeah, just that iodide ion, yeah. Iodide.
Wait, were you doing 14.11?
Yeah, that was number 11.
Oh, I spaced out.
Okay, I kind of skipped around on those catalyst ones. That would have made it confusing too, because I just went through them in the order that I was talking about catalysts. So again, nothing very complicated. I think once you read it and look at it and then look at those problems again, it will be pretty straightforward too. It might take a little practice in looking through those diagrams. So like you had pointed out, Caitlin, just make sure you find 2 trials that you can compare. Look for the thing that's not changing. Look how the concentration changes in relation to the reaction rate. That's going to inform what your exponents are. And then you can plug everything in from a trial just to find out what K is. So practice some of those, and I think you'll get the hang of it. You'll practice them. We'll look at them again next week, and I think that will make sense. So actually a fairly easy module once you get into it. I
didn't catch what to do for 14.11.
Oh, so when the catalyst is, so this is a homogeneous catalyst. So it's the same, in the same phase. It's all liquids. You've got peroxide, which is a liquid, and these iodide ions in there. And so with a catalyst, they're showing you the different steps. So those 2 reactants in step 1 react, and they produce some products, some water and some iodide ions. And then those 2 react, they become the reactants, and they show you what happens in step 2. They take those products, those are now the reactants, and they react again, and then you get 2 water molecules, the 1 oxygen molecule and the 2 iodide ions. So what you see is that iodide, while it did react, there was an intermittent step to where it reacted, but every time it's getting reacted, it's getting recreated again in the course of this reaction. So I have iodide, those 2 iodide ions there in the beginning, and then I see them there again at the end. So that tells me that's the catalyst, because it did not get used up in the reaction. It assisted the reaction in going faster, but in doing that, it was not used up itself. I feel like there's an analogy for life in there somewhere, like some kind of good object lesson or something. But anyway, so it assists everything in going faster. It lowers the activation energy. And then it's not used up in the process. It's still there at the very end. So you're just finding what's in the original reactants that's still there in the final products, in spite of all those in-between steps, what's still there at the end and didn't change. And that's going to be the catalyst. Good old chemistry.
Are we done early?
I think we are.
Hey, I was not expecting that because I yelled at you.
You started late too, so.
I'm sorry.
You don't have to be sorry. You get a little break. You guys have any questions that you can think of? You might have more as you interact with it a little bit. I put the homework up already. It's just the study guide problems. And again, I think I added maybe 4, but I think only 3 of the extra practice problems. So don't miss those, because I do want you to get those practice. I don't have your homework graded from last week. I apologize. I don't know that all of you sent it to me. I'll go back and check. I know I got it.
I might have forgotten. I'm gonna do it right now.
What's that?
I think I might have forgotten. What are we supposed to turn in?
It was your homework that you would have done before spring break.
Is it 13 extra practice problems?
It seems like it probably was. Yeah, it probably was the end of that.
Right now then.
Yeah, that feels like ages ago, doesn't it?
It really does.
Yeah, just send me a picture of that so I can give you guys credit for that. Yep. So not too heavy of a homework week. Hopefully chemistry shouldn't be a big burden to you this last few weeks. it's still something. Obviously you have to be doing work for it to
Yeah.
count. And I wouldn't even drastically worry about your hours. There's sort of unprecedented things going on, I feel like, in all of academia for all students, because I think even I think they did shorten the actual school year to like 160 days for public schools too. So I think if we finish out these 2 modules, you can call it a good chemistry year and feel like you did all the things you were supposed to do. You did a lot of chemistry work. So I will work on getting those tests graded. Again, just make sure you send me your work if you haven't sent it already. And Caitlin, I feel like you should have some opportunity to improve your grade. I can understand why you didn't take the test. That's reasonable because you did have a decent grade for sure. If you want to take like if there was a big one that you missed, I don't know, if there was one that was like working a problem out and write it out and work it out, I'd be willing to give you some points for that.
Okay.
Up your grade. I feel like that would be fair since everybody else got a very large opportunity to improve their grade. That would be a fair thing to do.
Did everyone get A's?
No, everyone did not get
Okay.
A as of this point. So, all right. So send me your work. I'll get those graded because I can.
First time you took it.
Who's talking? What, Emily?
Caitlin, what did you get the first time you took it?
Not an A.
What'd you get?
I got a B. But I figured I'd just leave it because
I will say, I feel like it was a hard test. I feel like it's a kind of test where like, yes, getting a B would be a grade to be happy with. It was, I mean, not hard. Like I didn't make it hard on purpose. I just think content wise, it is harder stuff. You're dealing with a lot of numbers and equations and stuff going on.
I know. My mom was like, Caitlin, you're not taking an opportunity to make it higher. And I was just like, I really just don't want to do it again.
Yes, I would have said anywhere from like, 85 to 95. Yes, definitely. Very good grade on that test. There was a lot going on. I will say I started looking at the corrections. There's a few questions that were actually almost exactly, maybe 2 that were actually the same. They were actually the same. I want to say 2. I know for one for sure there was a multiple choice that people still missed that I actually said it and here's what it is. And so stuff like that, I don't know, that's just hard. I don't know how to reconcile that for you guys. Like I want you to be super successful, but I also can't just it is almost handed to you. Like, here's the test, here was what the answer was, here's the test again, and the answer's the same and you still miss it. That's a hard, I don't know. But I will give you as many points as I can. I'll look at your work when you send that and get them graded and add those extra points in. Emily, I have all yours added except for looking at your work. And Abby, I think that's true for everybody. I think there's definitely, I sometimes noted on there, hey, I just need to look at your work so it's one that I'll look at and see, but there's still opportunity for some more points. So anyway, okay.
Have you thought about the lab section?
I have but not in great detail. I'm sorry, it has been super crazy at our house. I'm not trying to make excuses. Just I haven't, in all honesty, but I will. So I won't leave it as something to punish you guys in terms of not having the opportunity to bring that up. I'm probably leaning towards. I will say I don't think labs have been a strong suit for anyone except for maybe Emily. But and Emily, I certainly won't bring your grade down. My thought is just to take that section out because there's just not a lot. But I'll weight it in a direct, probably to homework, something that benefits everybody. I don't want to punish anyone. But I don't even, I'd have to look at it. I think that labs are one of your stronger areas, but I don't even know. I'd have to go, I'm speaking off the top of my head. Has everybody turned to all the labs that you do well in labs? If you had one missing, your lab grade would still be low, so it would still benefit you to take it out. But I don't even know if you do, so I don't want to say that. I'm not.
There's one lab that I was just really stressed and just didn't do it at all, and so it brought it way, 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 way down.
Or maybe if everyone has just one low lab grade, I can drop that low grade. I just need to look at it. It's hard to say that without actually looking at the grades, but it could be just drop the one low grade.
I never had a bad lab grade, ever.
Queen.
Then I wouldn't have to drop one for you. If you don't have a low one, I wouldn't drop one then. That would, so.
Extra credit.
There's many parts to the body. Everybody's got different things that they're really good at. So just rest in what you're good at. Some are good hands-on and some are good with memorizing and doing things on paper. All are just gifted differently. Takes all the parts of the body, right?
Yes, ma'am.
All right, guys. Have fun in your next class. Please message me if you have questions about it, okay?
Awesome.
All right. Talk to you later.
Thank you.
You're welcome. Bye-bye.
Bye.
Good dog you.
Just a second.